Okay, ladies and gentlemen, let's go ahead and finish up chapter 16. We're doing the fifth section, and this one is entitled uh, Chemical Reaction Spontaneity. In other words, does a chemical reaction take place on its own or not? This is part of the larger section in chemistry called thermodynamics. Right now, we learned about enthalpy and energy coming in and out of systems. Sometimes the systems can be just water or a substance. Sometimes they can be chemical reactions. Thermodynamics is a broader section of chemistry. And as you can see in the name, the term thermo is in there because of energy, and dynamics means kind of how energy moves and how energy moves things. So basically, I can subtitle this lesson here. Thermodynamics is what makes a chemical reaction take place. So if we look at a chemical reaction, let's say we have these two chemical reactions over here. Actually, the second one's just the reverse of the first. The first one says that calcium chloride is going to be mixed with sodium carbonate, and it's going to form sodium chloride and calcium carbonate. Okay, we learned that. Well, we learned chemical reactions way back in chapter 10. So this basically says you mix calcium chloride and sodium carbonate, and you get sodium chloride and calcium carbonate out of that. Okay. The question is, does that really take place? I mean, is it that we uh, get mixed calcium chloride and sodium carbonate, and then we get sodium chloride and calcium carbonate? Or is the reverse what actually happens? Do we take sodium chloride and put it with calcium carbonate, and we end up with calcium chloride and sodium carbonate? Is it in one direction, or is the reaction in the other? And that's what we're going to be learning about in this section. How do we know if a reaction takes place or if its reverse reaction takes place? We're going to learn about a thing called free energy, and the free energy is what's going to tell us. But before we learn about free energy is going to take into account two other quantities. The enthalpy that we already learned, whether energy comes out or goes in to a system, to a chemical system. And the second thing here on this slide we have is a thing called entropy. And um, entropy is represented by the letter S, the capital S. So we have enthalpy and entropy. Be careful because they kind of sound very similar to each other. Entropy, if you look at the first bullet point here, entropy is a measurement of the disorder of a system. So whereas enthalpy is how much energy is coming in or out, entropy is measuring how much disorder. Now, most of the time, we really don't think about measuring disorder, right? Whether your room is organized or whether it's a mess, we don't think about measuring that. But with entropy, we could. The more disorder, the higher the entropy of something, of a system. And whether that system be your, bedroom, whether it be my classroom, whether it be somebody's car and orderly they take it, or how random the particles are in a chemical system, that can be measured. Second bullet point here says that the units are usually in joules per mole Kelvin. I say usually because sometimes they're in kilojoules per mole Kelvin. Sometimes they can put them in joules per gram Kelvin. But the basic idea is the amount of energy per mole and per Kelvin. So the basic idea in this third bullet point right there is that the greater the entropy, the greater the disorder. And just like enthalpy, we don't care about the absolute entropy. Some people, if you get into like graduate school, you can go ahead and calculate. In your book, they talk about the different kind of uh, possibilities with playing cards and how much disorder there can be with a certain number of playing cards. And you can actually calculate the actual entropy. What we care about now, though, is the difference in entropy through certain processes. What is the difference in entropy? So we're not going to spend a whole lot of time on this stuff. We're just going to get to the basics so we can understand free energy. If you take a college class one day, you'll find that you're going to spend plenty of time uh, calculating entropies depending on different things occurring. Um, and I will kind of say this here is that In order to calculate entropies, there are four main processes that we have that goes ahead and changes entropies. And what we're looking for whenever we want an entropy change, we're looking for delta S. And delta S is the final entropy minus the initial entropy. Okay? So the four things that can change the entropy of a system, in other words, give you a delta S, give you a change in entropy, are volume change. If there's a greater volume, that means that there's more space for specifically gases. All of this could work with solids and liquids. It's mostly for gases. And there can be large entropy changes by changing the volume. Um, the bigger the volume, the more space, so the more random the particles can be. The smaller the volume, the more compressed it is, the less space, and so the less places where particles can be, so there's less randomness. There's less disorder, right? If you really kind of scrunch a gas down, there's not much place that those particles can go, so they're going to be in only a few choice places in the space. On the other hand, if you really open it up, then particles can be all over the place. So when volume increases, you have a positive entropy because your final entropy is bigger than your initial. When volume decreases, it's the opposite. Your sign of your delta S is negative. Temperature change, the hotter something is, the faster the particles are moving, and so therefore the more randomness there can be. So with the temperature change, when the temperature goes up, your delta S is positive. When something is cooled, temperature goes down, and your delta S is negative. Phase changes, when you go from a solid to a liquid, we know that liquids move around more than solids, so therefore your delta S is positive. When something melts, goes from a solid to a liquid, and it's positive when it vaporizes, when it goes from a liquid to a gas. The phase changes in the opposite direction give you negative entropies. Gas to liquid is negative, and liquid to solid is negative. There are equations that go with all these, but we're not going to get into them. They use natural log functions or logarithmic functions, which you guys probably haven't gotten into unless you're already in Algebra 3. And in second semester, maybe you've used some of the logarithmic functions, but we're not going to worry about them. Although phase changes are pretty easy. They're just like, the heat of fusion or the heat of vaporization divided by the temperature which it's occurring. But the other ones are a little more involved. For chemical reactions, the more gases you make, a chemical reaction can have a delta S that is positive, and it can have a delta S that is negative. And it could be the same sign as delta H, or it could be the opposite sign as delta H. It really depends on the reactants versus the products. What are you making? Are you making stuff that's more random or less random? If you are creating more gas particles, that means that you're going to have more random molecules with more random motions. And so therefore your delta S is going to be positive. If you're losing gas particles, then some of your reactants are gases, and they're being turned into solids, liquids, or aqueous substances, then your delta S is going to be negative. Okay, so we're not really going to be using a lot of equations. There are equations that go with this, but we're not going to be using a lot of equations for entropy that go with this. When you take a chemistry class in college, though, they will spend a good chunk of time just on entropy. Okay. There is one equation that we could use if we wanted to figure out the delta S of a chemical reaction. Just like there's enthalpies of formation from our last video, there's also entropies of formation. And those can be looked up also in a table like enthalpies of formation. So delta H is formation, we used last time. Entropies of formation, S subscript F, are also possible. And you can look up the entropies of formation of products, each one multiplied by its coefficient, and subtract the entropy of formation of the reactants, right? So products minus reactants, just like the enthalpies of formation, delta H's of formation. Okay. I don't think there's any problems that have us calculate that. We're just basically going to kind of give you entropy in this book. And that's kind of all we're going to cover. But I wanted to go over entropy because it is kind of a big part of our equation that we're looking at today. So let's go ahead and move. One thing to note is that entropy can be calculated also for the surroundings. So you can have a delta S of the surroundings, and its first bullet point right here shows that there is a delta S in surroundings. And that delta S surroundings is always the negative delta H of the system divided by T. Because the only way you change the entropy of the surroundings is based on the heat that comes up. And so sometimes we will want to look at delta S in surroundings and use that. You'll recall earlier in the chapter we learned the first law of thermodynamics, which was that energy cannot be created or destroyed. And from there, we got that Q of the system is equal to negative Q of the surroundings. There is a second law of thermodynamics, and that is the second law of thermodynamics says for any spontaneous process, the entropy of the universe is increasing. Now, the entropy of the universe, what is that? Basically, what this says is that naturally spontaneous processes occur when the entropy of the universe is positive, and the entropy of the universe is or delta S of the universe is the delta S of your system, whatever that system is doing, plus the delta S of the surroundings. And you think that these two are the opposites, but they're not necessarily. If the surroundings is much bigger than the system, then your delta S of your system might be much larger than the delta S of the surroundings, because the small amount of heat that goes into the surroundings might not make a big difference in the entropy of everything outside you. But that heat or whatever processes that occurred inside may have a big effect on a small system. So delta S of the system and delta surroundings are usually actually not the same. And according to the second law of thermodynamics, when you take your delta S of your system, add it to the delta S of the surroundings, usually they're opposite signs, but they're not the same magnitude, they're not the same size. If the delta S of the universe is positive, then your process is actually spontaneous. And when it comes down to it, that is what's making a chemical reaction take place. The chemical reaction itself is changing the entropy of the chemicals, but it's also changing the entropy of the surroundings. And if the entropy of the system is positive and greater than the negative negative value of the surroundings, then it's spontaneous. If it's smaller, if it creates more entropy in the surroundings, or at least some more negative entropy in the surroundings, and it's positive in the system, so your answer ends up being a negative, then it's not spontaneous. Okay, that's what we get from the second law of thermodynamics. There's all kinds you can go into all kinds of deep stuff about the second law of thermodynamics, which I won't go into, here. I even kind of base my whole kind of I don't want to call it religious, but spiritual beliefs based on this whole second law of thermodynamics, which I'm not going to get into, but you can go to that much depth on this whole idea. Let's find a useful way of using it. Okay. We're going to go ahead and turn the entropy change of the surroundings into a new quantity. This new quantity is called Gibbs free energy. And the way we do that is, if I go back over here, you'll recall that the delta S of the surroundings is just minus delta H over T. So if I were to substitute the negative delta H over T here, and I were to go ahead and then divide both sides of the equation by T. I'm sorry, multiply both sides by T. Then the T would cancel here, leaving you with negative delta H here. We'd have T times delta S here. Then we'd get something like negative delta S over T here. And that is what this Gibbs free energy is. So we have this new quantity. And this new quantity came by taking the last equation. And I know I'm going over this kind of quickly, but we really don't need to know the derivation. I just want you to know that this is where it came from. That the free energy is represented by delta G. As you can see, there's a delta G here. So how does the Gibbs free energy change? And the free energy is a quantity that tells how much energy must be put into a reaction in order for it to occur. I guess that's the way you can kind of think about it. Delta G is, hey, I have a chemical reaction here. If I want this reaction to occur, because it's not occurring spontaneously, I have to put this much energy in. Okay. When the delta G is negative, if you look at the second bullet point here, when the delta G is negative, the reaction is spontaneous. Okay, because think about it. We just said that this delta G is a quantity that tells us how much energy has to be put into a reaction in order for it to occur. How much do we have to put in? So if your delta G is negative, you don't have to put anything in. It just happens automatically. So when delta G is negative, the reaction happens automatically, and the reaction is called spontaneous. When delta G is positive, then the reaction is not spontaneous. As I said earlier, that's how much energy we have to put in order to get the reaction going. It actually turns out that when delta G is positive, it's the reverse reaction that is spontaneous because it would have the opposite sign. So delta G is negative, the reaction is spontaneous. Delta G is positive, the reverse reaction is spontaneous, and our reaction as written from left to right is not spontaneous. And there are times when delta G actually equals to 0. And when delta G equals to 0, the reaction doesn't go from left to right or from right to left. The reaction is at what we call equilibrium, where the amount of reactants turning into products is the same as the amount of products turning into reactants. Okay, or there's a whole chapter coming up on equilibrium, so we'll get to that later. So that's your delta G. That's what delta G means. The question is, how do you calculate it? Here's the answer. I've got an equation here for you. As I mentioned to you guys, we took that delta S of the universe equals to delta S of the system plus delta S of the surroundings, and the fact that delta S surroundings was minus delta H over T. So if we just go ahead and play around with it a little bit, you get this equation right here. The second bullet point. Delta G is equal to your delta H minus T delta S. Remember, we get we got the delta G here because we took the negative delta H. Sorry, we got the delta H here because we took negative delta H over T and we multiplied it by T, got rid of the T. We actually multiplied by negative T, positive delta H. Then we also had delta S in our other equation. If we multiply by negative T, you get negative T times delta S. And the left-hand side was delta S of the universe. If we divided it by negative T, we get delta S of the universe over T. Well, that's what delta G is. Delta G is the negative delta S of the universe divided by the temperature. Okay. Now you don't have to know all that. You just have to know here's the equation that we're going to be using for our problems today. The units are in joules per mole. A lot of times they're in kilojoules per mole, actually, but basically any type of energy unit over mole. Don't have to worry too much about this part. There's also an equation where you can figure out what's called a delta G, a standard delta G, and it's also one of those things where you can look up G's of formation of products minus G's of formation of reactants. But this is only good at 298 Kelvin because since delta G is temperature dependent, the delta G at 298 Kelvin is going to be different than delta G at other temperatures. Okay, don't worry about that. So in order to figure out if your reaction is spontaneous, you got to look at the delta H, and you got to look at the delta S, and you got to look at the temperature. Plug those into this equation. If your delta G is negative, that means your reaction is spontaneous. If your delta G is positive, it's not. And if the delta G is 0, that means that you're at equilibrium. Okay? Let's take a look at this chart right here. This chart basically tells you that certain reactions are always spontaneous. Sometimes they're spontaneous at lower temperatures, sometimes they're spontaneous at higher temperatures, and sometimes they're never spontaneous. And what makes them either always spontaneous, spontaneous at low temperatures, spontaneous at high temperatures, or never spontaneous? It really depends on the sign of the delta H over here in this column and of the delta S. Temperatures are going to be in Kelvin, so temperatures are always going to be positive. But if we look at this chart is examining what kind of sign you're going to get for delta G, depending on the signs of delta H and delta S. So let's take a look at the two extreme examples first. Always spontaneous, which means the delta G is always negative. And the last one here, never spontaneous, because the delta G is positive. When your delta H is negative and your delta S is positive, your reaction will always be spontaneous. Because think about it. If you have a negative number, right, this equation is delta G is delta H minus T times delta S. First off, let's go ahead and multiply the T delta S's. If your delta S is positive and T is positive, when you multiply two positive numbers, you always get a positive number. So if you start off with a negative number and you subtract the positive number, right? Negative 5 minus, it really doesn't matter. Negative 5 minus 3. It's going to become more negative, and it'll always give you a negative answer. So that's why when your delta H is negative and your delta S is positive, you always get a negative delta G, and your reaction is always spontaneous. Now, if you look at the opposite signs for delta H and delta S, when delta H is positive and delta S is negative, you always get a positive delta G. So once again, let's take a look at the product of T delta S first. So if your T is always positive, as we said before, right? Kelvin always has positive temperatures. If your delta S is negative, then a positive times a negative is going to give you a negative number. So if you start with a positive delta H, start with a positive number here, and you subtract a negative number. By subtracting a negative number, that's like adding. So if you start off with positive 10 and you subtract a negative 5, that's like 10 minus negative 5 is the same as 10 plus 5. That's 15. And there's no number you can plug in here that's going to give you a negative answer for delta G here. So when a delta H is positive, when a chemical reaction has a delta H that is positive and a delta S that is negative, then you always get a positive delta G, and your reaction is never spontaneous. When your delta H is negative and your delta S is positive, you always get a negative answer for delta G, and your reaction is always spontaneous. Now, the other one's a little trickier, because when the signs are the same on both of them, delta H and delta S, there's times when your reaction is spontaneous and times when there isn't. Okay, so let's kind of take a look at this one here real quickly. In order to get a negative delta G, what you're going to do is start with a negative number. Then you're going to subtract a negative number. So whether you end up with a positive really depends on whether the first negative is bigger or the second negative is bigger, right? The T times delta S. If your delta S is negative, T times delta S is going to be negative. You start off with negative 10, but then you subtract the negative 15, then you're going to end up with positive 5, right? Negative 10 minus a negative 15, the same thing as negative 10 plus 15. That gives you a positive 5. But let's say you start off with negative 10 and you subtract negative 5. Let's say this product is just negative 5. So negative 10 minus a negative 5 is still going to give you negative 5 as your answer. So what your sign of your delta G is here really depends on how big your delta H is and how big your delta S or T delta S is. Which one's bigger? Which one wins kind of the battle? Now, for a chemical reaction, delta H is always, it's going to be always constant. So you have one delta H, And the same thing with delta S. What you can change is the temperature. So whether the T delta S value is more negative than the delta H can be changed by changing the temperature. And as you get to smaller temperatures, that means your T delta S value will be a smaller negative, and so therefore it will be overwhelmed by the delta H here. And I'll show you just a little bit um, what we some examples of how we can do that. Um, Same thing when you have positive delta H and positive delta S. Once again, we want the reaction to be spontaneous when delta G is negative. Now, T times delta S, since they're both positive, is going to be a positive number. So you're going to start with a positive number, subtract the positive number. Whether you get a negative answer for the whole for delta G really depends on how big T delta S is versus delta H. So if your delta H is bigger than your T delta S, then it becomes positive and it's not spontaneous. But if your T delta S is bigger than your delta H, then you're subtracting a bigger number from a smaller number and you're going to get negative delta G. So the bigger your temperature, the bigger your T delta S, and therefore the bigger number you'll have to subtract from your delta H. Okay, let me go ahead and show you on a spreadsheet here how that can work. So on this spreadsheet, hopefully you can see it. I know it's kind of small. I'm trying to get everything in here. I've got two situations here. We're using this equation. Delta G is equal to delta H minus T delta S. Okay, and so what I have here is a situation where both delta H and delta S are positive. And I just chose a delta H, 45.3 kilojoules per mole, and a delta S, 126 joules per mole. And what I did is I plugged those into the equation. I turned the delta H, by the way, into joules per mole Kelvin by multiplying by 1,000. So that way, they are both in joules per mole or joules per mole Kelvin. So I plugged those into here. And then I plugged in different temperatures. This is one of the great things you can do with the spreadsheet. So what I have here is at 10 Kelvin, using these numbers for delta H and delta S, I plug them in and I multiply this delta S by 10, and I get 44,040 joules per mole Kelvin. And watch what happens as the temperature increases. My temperature increases, my delta G gets smaller and smaller and smaller, because as the temperature is increasing, I'm subtracting a bigger number. Delta H doesn't change, but the number I'm subtracting from delta H is getting bigger because the temperature is getting bigger. So as the temperature gets bigger, eventually we get to the point where at about 370 degrees, we go into a negative delta G. So here, about 350, the delta G is still 1200. At all these temperatures, 350 and below, their delta G is positive, so the reaction is not spontaneous. Once you hit 370, now you'll notice that your delta G is negative, and higher temperatures above that, your delta G is going to get bigger and bigger, or more negative and more negative and more negative. So therefore, it's all going to be spontaneous. So all those are temperatures at which the reaction is spontaneous. So not spontaneous down here at low temperatures, spontaneous at higher temperatures. This was me just plugging in these numbers here into delta H here, delta S, and just plugging in a different temperature. Spreadsheet did it automatically. I didn't do a lot of work. On the other hand, if you have negative delta H and negative delta S, the opposite occurs. I'm going to plug in 10 Kelvin here for the temperature. And I'm going to multiply it by, in this case, I used negative 227 joules per mole Kelvin, and I used negative 53.2 kilojoules per mole. Plug that in here. And as I plug that in, as the temperature increases, first off, at 10 degrees Kelvin, my delta G is negative 50,930 joules per mole Kelvin, or 50.9 kilojoules per mole. It's negative, so it's spontaneous, as opposed to over here, where our delta H and delta S were positive at 10 degrees Kelvin. My delta G was positive, so it's not spontaneous. But here at 10 degrees Kelvin, because the signs are the opposite, it's negative, and so therefore my reaction is spontaneous. And as my temperature goes up, my delta G also starts going up. And in other words, less negative, less negative, until you get to a point where about 250 Kelvin, you finally get to a positive delta G. So this reaction is actually negative and therefore spontaneous at lower temperatures, up in maybe a little bit above 230 degrees. It'll be spontaneous. Above that, it won't be. Now the answer is the delta G start getting bigger and bigger and bigger. Okay. Somebody might ask, at what temperature specifically is this reaction going to go from being spontaneous to not? And that's the temperature at which delta G is 0. And you can find that. And I'll do that on a sample problem, in the sample problem videos. When delta G is 0, that's the temperature at which, above that is spontaneous, below is non-spontaneous, or vice versa. And all you do is solve for what that temperature is. You plug in 0 for delta G, plug in the delta H and delta S. And all you have to do is solve for T. And T is the equilibrium temperature, and the temperature at which above will either be positive or negative, and below will be the opposite. Okay. So I hope this helped kind of straighten out what we're talking about in this section. I'll do a few sample problems. The problems really aren't that hard. You plug into this equation, but it's a few tricky things like making sure you got the right units that match. So I'll put up a couple of videos. Okay. All right. Thanks for listening.